In this video, we start chapter 8, where we study the ellipsoid method. Here we have a list of the sections that we're gonna see. First, we go back to the topic of computational complexity, and we will formally define a polynomial time algorithm under the bit model. Next, we're going to introduce the key geometric result behind the ellipsoid method. This will allow us in the next section to fully develop the ellipsoid method. First, we will see how the ellipsoid method can solve linear programming feasibility problems. And next, we will see how it can also be used for optimization problems, so to solve linear programming problems. Finally, we will also see how the ellipsoid method can be used to solve linear programming problems with exponentially many constraints. In particular, we will see that the ellipsoid method is able to solve any linear programming problem in polynomial time. On the other hand, the simplex method is not always able to solve a linear programming problem in polynomial time, and this is because, as we have seen, it may require an exponential number of pivots. So from a theoretical perspective, the ellipsoid method is efficient and the simplex method is not efficient. Unfortunately, the ellipsoid method is not efficient also from a practical point of view. Therefore, its interest is only theoretical. It is important to notice that the ellipsoid method is the first known algorithm that is able to solve linear programming problems in polynomial time. So it demonstrated that linear programming is efficiently solvable from a theoretical point of view. This is very important because once a problem is shown to be efficiently solvable from a theoretical point of view, usually new algorithms follow which are efficient both from a theoretical point of view and from a practical point of view. This was in fact the case with linear programming problems. In fact, after the introduction of the ellipsoid method, new algorithms known as interior point methods were introduced. These algorithms make use of the new insight provided by the ellipsoid method to obtain novel algorithms that are practical both from a theoretical perspective and a practical point of view. So now let's get back to computational complexity, where now our main task is to define polynomial time algorithms, which are the algorithms that informally we say are efficient from a theoretical point of view. If you remember, in section 1.6, we've already discussed the notion of efficient algorithms. In this section, we continue that discussion in order to give a formal definition of polynomial time algorithms under the bit model. Most of the times in the literature, when researchers discuss polynomial time algorithms, this is the notion that they're talking about. The first concepts that we need to understand are the concepts of a problem and of an instance of a problem. Informally, we already know the difference between a problem and an instance. For example, we know that linear programming is a problem. On the other hand, the specific linear programming problem, where we minimize 2x plus 3y subject to x plus y less than or equal to 1 and x and y non-negative, is an instance of the linear programming problem. Definition 8.1 tries to formally define instances and problems. An instance of an optimization problem consists of a feasible set f and a cost function c from f to r. Here we're implicitly assuming that the objective is to minimize the cost function c over all vectors in f. On the other hand, an optimization problem is defined as a collection of instances. In particular, instances of a problem must be described according to a common format. For example, instances of a linear programming problem in standard form can all be described by listing the entries of the constraint matrix A, of the right-hand side vector B, and of the cost function C. Note that our definition 8.1 is not really formal, but I don't want to go into more details to give you a more precise definition, and in any case this definition will be enough for what we need. In particular, notice that definition 8.1 is a chicken and egg definition. This is because I am defining instance using the word problem and I'm defining problem using the word instance. And of course, this is enough to raise a red flag that tells us that this definition is not formally correct. The next concept that we need to define is that of size of an instance. The reason we need to define the size of an instance is that some instances of the same problem are clearly larger than others. And so it is reasonable to expect that the same algorithm will take much longer on these instances with respect to the smaller instances. Our definition of a size of an instance essentially tells us that the size of an instance is the number of bits that you need to store your instance in your computer. Formally, the size of an instance is defined as the number of bits used to describe the instance according to a pre-specified format. In particular, for a linear programming problem in standard form, the size of an instance is the number of bits that you need to write down the matrix A, the vector B, and the vector C. In order to understand the size a little bit better, let's see the size of an integer r between 0 and a given upper bound u. So we need to see how many bits we need to represent such an integer r. Essentially, we write down our integer number r in its binary representation. So we can write it as a binary number plus a binary number times 2 plus a binary number times 2 to the second, and so on and so forth. In particular, it is simple to check that in this sum you need at most the floor of the logarithm of u terms. Therefore, your integer r can be written as the sum of ai 2 to the I, where each ai is 0 or 1, and where I goes from 0 to the floor of log u. Hence, we can represent our integer number r only using the 0, 1 scalars ai. The total number of these scalars is the floor of log u plus 1. Therefore, we need the same amount of bits to represent r. Now, if instead we want to represent an integer whose absolute value is bounded by u, then we need only one additional bit for the sign. Therefore, the total number of bits will be the floor of log u plus 2. As always, we are only interested in the asymptotic behavior of this quantity. Therefore, the key message here is that we only need big O of log u bits. Let's see an example. What is the size of an instance of matrix inversion? An instance of the matrix inversion problem is an n by n matrix capital A. Let's assume that the absolute value of all the entries in A is upper bounded by some number capital U. We have just seen that the size of each entry of A is big O of the logarithm of U. However, now we have n square entries in our matrix A. Therefore, the size of our instance will be n square times big O of log u, and this is big O of n square log u. Now let's see another example. We consider a linear programming problem in standard form. Here, an instance is a little bit more complicated. In fact, we have our m by n constrained matrix A, we have our m vector of right-hand sides B, and our n vector of the costs C. Also here, we assume that the absolute value of every element in A, B, and C is upper bounded by some number u. Now the size of every entry is big O of log u, but now the total number of entries is mn for the matrix A, m for the vector B, and n for the vector C. Therefore, the size of an instance is at most mn plus m plus n times big O of log u, and this is simply big O of mn log u. As I've already mentioned, it is natural to think that when an algorithm is applied to instances of larger size, it will take longer to terminate. This is why the running time of an algorithm is normally expressed as a function of the size of the instance to which it is applied. So now let's discuss the running time of an algorithm. In section 1.6, we already discussed the running time, and there we defined it as the total number of operations carried out by the algorithm from beginning to termination. In particular, counting only the number of operations performed essentially means that we're assuming that every operation takes unit time. Then this model is in a sense the simplest one that you can think of, and it is called the arithmetic model, exactly because you just count the number of arithmetic operations. In this section, however, we discuss a different model, which is called the bit model. On the one hand, this model will be more complicated, but on the other hand, it will mirror more closely what happens in reality. Therefore, it will be more meaningful. The main difference between the bit model and the arithmetic model is that in the bit model, we count the number of single bit operations. So every instruction is decomposed into a set of elementary instructions that operate on single bit numbers. And every such elementary instruction is assumed to take unit time. This model is much more realistic than the arithmetic model. In fact, the bit model essentially mirrors what happens in our computers. The drawback is that now calculating the running time will be much more complicated because we need to keep track of the number of digits of the numbers that the algorithm computes. We are going to denote by T of S the worst case running time of some algorithm over all instances of size S under the bit model. Now we can say that an algorithm runs in polynomial time under the bit model if there exists an integer k such that T of S is big O of S to the k. So what are the differences between polynomial time algorithms under the bit model and polynomial time algorithms under the arithmetic model? The first one is that in the bit model, we measure differently the running time, because in the bit model we only consider single-digit operations. The second key difference is that under the bit model, the running time is a function of the size of the problem. On the other hand, under the arithmetic model, the running time is just a function of the number of numbers in input. For example, for linear programming problem, in the arithmetic model we measure the running time as a function of n and m only, and not as a function of the size. On the other hand, the size is a function of n and m, but it is also a function of the magnitude of the numbers in input. It is then clear that it's much easier to measure the running time under the arithmetic model with respect to the bit model. However, the next fact shows us a very interesting link between the running time under the arithmetic model and the running time under the bit model. Suppose that an algorithm takes polynomial time under the arithmetic model. Furthermore, suppose that on instances of size s, any integer produced in the course of the execution of the algorithm has size bounded by a polynomial in S. Then the algorithm runs in polynomial time under the bit model as well. This fact is extremely useful to show that an algorithm is polynomial time under the bit model. In fact, you then have to show two separate things. First, that it is polynomial time under the arithmetic model, which is an easier task, and then you need to look separately at the size of the numbers that appear throughout the execution of the algorithm. It is interesting to notice that most of the proofs in the literature that show that an algorithm is polynomial time under the bit model use this fact. But how can you prove this fact? Essentially, you need to show that under the assumptions of the fact, every arithmetic operation can be carried out by a subroutine that takes polynomial time under the bit model. An example of an algorithm that runs in polynomial time under the bit model is Gaussian elimination. Gaussian elimination is an algorithm that inverts the given matrix. So it is an algorithm to solve the matrix inversion problem. We have already seen in section 1.6 that the number of arithmetic operations performed by Gaussian elimination is big O of n cube. Therefore, it is a polynomial time algorithm under the arithmetic model. On the other hand, it can be shown that Gaussian elimination only produces numbers whose size is bounded by a polynomial in the size S of the input matrix. Therefore, using our fact, Gaussian elimination is a polynomial time algorithm under the bit model. Therefore, matrix inversion can be performed in polynomial time under the bit model.